From the size of the smallest atom to the numbers and shapes of the vast universe, we use data to run, power, and improve our world. This set of data should be interpreted and analyzed for it to be useful to humankind. Data analysis is an important tool for us to be able to understand and acquire information that is useful in our daily lives. It is a tool for decision making. It helps us answer our questions, helps us predict the outcomes for events, and it is a tool for change and improvement. In interpreting and analyzing data, there are a lot of software that are applicable. But today, we will use the mini tabulation statistical software, or commonly known as the Minitab application. So what is Minitab? Minitab is a software application that is useful in statistical concepts and calculations. This was developed in 1972 by three Penn State University statistics professors to make the statistical calculations easier and faster. It provides a simple, effective way to input, manipulate statistical data, distinguish patterns and examples, and afterward predict and answers current issues.
Hello everyone, my name is Kenneth and I'm here today to teach you the basics of Minitab interface. For that, kindly look at your right screens. The Minitab interface is divided into 5 parts, namely the navigation pane, the output pane, data pane also known as the worksheet, the command line and history pane combined, and the status bar. In the navigation pane, your output titles are displayed. It is sorted from oldest to newest. It is used to toggle between your outputs. The output pane, it is where your outputs are displayed. Outputs like graphs and tables are shown. In the data pane, also known as the worksheet, it is where you input your data to be analyzed. While in the command line and history pane combined, it is where you type your commands and at the same time view the previous commands used in your projects. And lastly, in the status bar, it is used to show or hide the multiple panes. Now, put your mouse pointer into the menu bar. There are lots of options in the menu bar, but look at the Stat tab, the Graph tab, and the Data tab. The Stat tab contains basic statistical tools. The Graph tab contains the options for your output, while the Data tab contains the options for manipulating your data in the worksheet. For this video, I want you to focus heavily on one-way ANOVA and create a normal probability distribution charts.
Good day everyone. Today we will have an example of an ANOVA in Minitab. An engineer wants to compare the hardness for 4 blends of paint. 6 samples of each paint blend were applied to a piece of metal. The pieces of metal were cured. Then each sample was measured for hardness. In order to test for the equality of means and to assess the differences between pairs of means, the analysis used one-way ANOVA with multiple comparisons. Now, one-way ANOVA is used to determine whether there are any statistically significant difference between the means of 2 or more independent variables. Now, here on Minitab, we go to the status bar, click ANOVA one way, then we select the response data that are in one column for all factors levels. On our response, we select the hardness, click select. On our factor, we click for the paint or on the C1 section, then select. In our comparison, we have 3 choices. We have the Toki, the Fisher, and the Donut. The Toki compares every mean with every other mean, while the Donut is a test compares every mean to a control mean. Well, the Fisher is employed when the sample size are too small. So here we click the Toki for our example. We click the results on interval plot for differences of means, the grouping information, the test, then click OK, then OK. Then on Minitab, they will calculate the results, then we have these results.
So I will be interpreting the results in our previous problem. So the first step in analyzing the results for one-way ANOVA problem is to determine the null hypothesis and alternative hypothesis. So the problem wants to test the means of each sample of the four blends of paint in terms of hardness. So as you can see from the results, the null hypothesis is that all means are equal, or should we say that there is no significant difference between the means of metal hardness among the four blends of paint. And our alternative hypothesis is that the means are not equal, which will show that there is at least one significant difference on the means. I indicated the word at least one because it can be that among the four blends of paint, there is at least one blend that differ or significantly different from the other, which has a higher or lower mean. This will be shown later on the results of the post-hoc test or multiple comparisons test. So as you can see here, our alpha was set into 0.05. So this level of significance will help us to determine if we reject or not our null hypothesis. So in order to test this, the main points that the main points that you should observe in this ANOVA table is the F ratio and the P value. The F ratio is the ratio of the mean of squares between and the mean of squares within, meaning it enables us to see how far or how close are the means to one another. This F ratio will lead us in determining our P value. The P value is the one that will be compared to our level of significance. If our P value is less than the level of significance, then we will reject our null hypothesis. As displayed, okay, our F value is 6.02 and our P value is 0.004, which is less than our alpha. With this result, we can say that there is enough reason for us to reject the null hypothesis. This further concludes that there is a significant difference among the means of metal hardness of the four blends of paint. Okay. So now, we already know that there is a significant difference among the means. But for us to know which among the four blends of paint cause this difference, we will proceed with the results of the multiple comparisons test. Okay, as revealed, there are two means of the blends that differ from the other group. The means of blends 4, 1, and 3 are significantly different with the mean of blend 4, and the means of 1, 3, and 2 are significantly different with the mean of blend. Okay, I will repeat that. So, the means of blend 4, 1, and 3 is significantly different with blend 2, and the means of blend 1, 3, and 2 is significantly different with the mean of blend 4. So blend 2 and 4 are significantly different from each other because as you can observe with the mean, blend 2 has the lowest mean of 8.57 and blend 4 has the highest mean of 18.07. This large gap between the two blends, okay, the means of the two blends, is the reason as to why there is a significant difference among the blends of paint. This is supported in this graph here below. So wait, we will just zoom out so that we can visualize our graph here, the only comparison that does not touch the zero line is the comparison between blend 4 and blend 2, which means that they are significantly different from each other. So this is also shown in the graph of the interval plot of hardness versus pain. Okay. So same as with this graph, the interval plot of hardness versus pain, we can also show the difference between the means of the blend. So for example, if we put a horizontal line here, it will touch blend 1, 2, and 3, which means they are not significantly different from each other. So same as with when we put a line here, okay? Same as when we put a line here, in the top, it will touch blend 1, 3, and 4, which means that they are not significantly different from each other. So, all in all, we can say that only blend 2 and blend 4 are significantly different from each other, which further leads us into a conclusion that blend 4 is sort of more effective than blend 2 or the other means as well, because blend 4 has the highest mean among the 4 blends in terms of metal hardness.
Our next problem is all about normal distribution. So this is one of the examples of normal distribution problem. Let x represent the duration of an 8-week baby smile, where x is normally distributed with mean 9.1 seconds and standard deviation of 2.2 seconds. What is the probability that a randomly chosen 8-week-old baby smile between 6 and 12 seconds? In solving this kind of problem, you need to understand and analyze what is asked in the given problem. So in this case, we need to find the probability that a randomly chosen 8-week-old baby smile between 6 and 12 seconds. To solve the problem, you need to list the given values in the given problem. We had mean is 9.1 seconds and the standard deviation of 2.2 seconds. So what is asked in the problem? The probability between 6 and 12 seconds. In solving the normal distribution, x is normally distributed with mean and variance. In our problem, we only had standard deviation, and we all know that the square root of standard deviation is the variance. So we get x is normally distributed with mean, which is 9.1 and 2.2 squared seconds. In standard normal distribution, the probability or the mean and variance should be 0 and 1. So in this case, you need to convert the mean and variance into 0 and 1. So that method or that process is called standardization. The standardization is z is equal to x minus mean over standard deviation. As stated in the problem, we had two value of x, since it's stated between x and 12. So it obviously we got the two value of the z-score. So z is equal to x minus mean over standard deviation. So in this side, if we let x is 12, so 12 minus mean, which is 9.1, over the standard deviation is 2.2, we get the value of z-score is 1.32. And the other side, if our x is 6, so 6 minus mean, which is 9.1, and the standard deviation of 2.2. So the value of the z-score is negative 1.41. So therefore, our standard normal distribution is z is normally distributed with 0 and 1. So after getting the value of the z-score, we need to find the p-value. So in solving the p-value, we just need to write the we just need to to write the probability that we're going to find. The probability of 6 less than x less than 12 is equal to the probability of z less than the value of the z-score that we already got, which is 1.32, minus the probability of z less than negative 1.41. So the value of this z-score is you need to look in the standard normal distribution table. So if you're going to find in the table, the value of z of 1.32 is 0.90658 minus the value of z of negative 1.41 is 0.07927. If we subtract each other, we got 0.82731, or it's just 82.73%. So the probability of randomly chosen 8-week-old baby smile between 6 and 12 seconds is 82.73. If we want to plot this z-score value in the standard normal distribution graph, this is what we look like. The whole area of the curve is 1, and the negative side of z-score, this side, and this side is the positive side of z-score. And the center is the mean, which is 0. So, as we can see, the value of z, 1.32, is positive. So, we assume this side is 1.32. And the other side is negative 1.41. If we subtract this 1.32 and negative 1.41, the left area, this area, is the probability of the randomly chosen 8-week-old baby smile between 6 and 12 seconds.
After you manually solve the problem, you need to create a graph to check whether your answers correspond to the result of the Minitab. First step in making the graph is you go to Toolbar, click Graph, choose Probability Distribution Plot since we are looking for the probability of the smile of the 8-week-old baby between 6 and 12 seconds. Click View Probability, then OK. In the distribution box, choose normal distribution since we are using normal distribution. Since our mean and standard deviation is already given, all we need to do is fill. Our mean is 9.1 seconds, and we have a standard deviation of 2.2. In the shaded area, click X value since the problem is using X values not standardized. And then click middle since we want the proportion of 8-week-old babies with a smile duration between two values. In X value 1, type 6, and in X value 2, type 12 from the 6 to 12 seconds interval, then click OK. As displayed in the output pane, this normal distribution graph has a probability of 82.69%, which means that our answer, the result of our manual solution corresponds to the result of our graph. Our manual solution has a probability of 82.73%. The slight difference is reasonable enough since we rounded off our values. Thus, we can say that there is 82.69% probability that a randomly chosen 8-week-old baby smiles between 6 and 12 seconds.